remember what we were doing? We were talking about how to solve systems of linear equations. Systems of linear equations, right? And remember that the idea was that if you have a system, then you can reduce it to an equivalent system, right? You can reduce it to a system that maybe it's not the same system, but it has the same solution set, right? So you reduce it down to a system whose solution set is obvious, and then well, you do that via operations that don't change the solution set. So at the end, you say, well, the solution set of this system is blah, and that's the same as the original one, right? That's the same as the original one, because all the things that we did didn't change the solution set. Okay, and so that process was called Gaussian elimination, right? And the result of the process was called row echelon form. Row echelon form. Okay. I never told you what row echelon form was exactly. There is sort of a long description of what row echelon form is. I can write. Let me just sort of write it out quickly. So one, all non-zero rows. All non-zero rows are above any rows of all zeros. So two, each leading entry. I should say I got this out of the book by Kenneth Lay because I couldn't find my textbook this morning from Leon. So each leading entry in a row is in a column to the right of the leading entry of the row above it. And three, all entries in a column beneath a leading entry are zeros. Okay, so let me just pause while you guys write. Looks like people are ready. Yes?
So row echelon form really refers to the equation?
Row echelon form refers to the form of the matrix.
Oh, okay.
The matrix, you've taken the matrix and then you've changed it into the simpler form. That form is called row echelon form. Okay, so last time we started off with this, large matrix, 2, -4, 2, -2, 2, -4, 3, -4, 4, -8, 3, -2, 0, 0, -1, 2, 0, 0, 0, 0. Right? We started off with this guy. We did Gaussian elimination on it, and we ended up with this matrix: 1, -2, 1, -1, 0, 0, 0, 1, -2, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay, so this was our original matrix, and then this is the matrix in row echelon form. Yeah. Okay. So you see, right, the rows with all zeros in them are at the bottom, right? If you look at the leading entries, so what they mean by the leading entries are the first non-zero entries. So the leading entries are moving to the right, right? So you don't have any leading entries above other leading entries, and this one is here, this one is farther to the right than the other guy, right? all entries in the column beneath a leading entry are zeros, right? You use the pivot to clear out all the entries below it, right? So these guys are all zeros. 0, 0, 0, 0, 0, 0, right? And so that's real echelon form. Let me make a remark that I'm not gonna explain. We can explain it later. That in fact no, forget it. I can make that remark yet. Say it later. Okay. So so this is what we finished up with last time, and people were saying, well, look, this isn't in strict triangular form. It doesn't have a unique solution, right? So how do you describe the solution set? So you think, okay, well, this corresponds to what's system? This is the system x1 minus 2x2 plus x3 minus x4 equals 0. X3 minus 2x4 is equal to 0, right? Right. So this is the an underdetermined system, right? We use some language. We call these guys corresponding to the leading entries the lead variables. Okay, so x1 and x3 are called the lead variables. Okay, and the other guys, x2 and x4, are called the free variables. Okay. And so you have the system. You say, okay, well, what do I need? What do the solutions look like? What do the solutions look like? What are the solutions? You say, okay, well, you notice that you can solve. So say, okay, well, look, if I say x1 plus x3 is equal to 2x2 plus x4. So let me express the free variables, the lead variables in terms of the free variables. Okay. x3 is going to be 2x4. Okay. I see that, x3 has to be 2x4, right? And that x1 plus x3 has to be 2x2 plus x4, right? Which together gives me that x1 has to be 2x2 minus x4. Okay, so the point is that, and this isn't that exciting, but that the lead variables can be expressed in terms of the free variables, right? Okay. And as long as this happens, right, as long as x1 equals 2x2 minus x4 and x3 equals 2x4, then this system is satisfied, right? So all solutions, right? The solution set is thus anything of the form all 4 tuples of the form 2x2 minus x4, x2, 2x4, and x4. Okay. So anything that looks like this is okay. Yeah, no.
So say if the task is if the problem is to solve an equation, would we just give an answer in this form, or?
Yeah. So if they say what's the solution set of the system corresponding to this matrix, you'd work it out. You say, well, the solution set is the collection. Can't draw. Is the set of vectors. Right, the set of vectors that look like where x2 and x4 can be any numbers, right? So this would be the solution set. solution set is thus this thing here. Okay, and so you see it's actually a two-dimensional set. It's a two-dimensional set. If you think about it geometrically, and we'll sort of make this clearer later, you can actually express this vector. I'm going to sort of jump a little bit, but I hope you allow me to do it. You can express this vector. You could also express this vector as x2 times 2, 1, 0, 0 plus x4 times negative 1, 0, 2, 1, where x2 and x4 are in R. That is, you're taking these two vectors in four-dimensional space, and you're multiplying by numbers, and you're combining them together. So we'll make this clearer later on, but what it is really you've got these two vectors in space, and you're taking all combinations of them. So it's the plane in four-dimensional space that contains these two vectors. Okay, that's determined by these two vectors. Okay, so really it's a two-dimensional solution set. Okay, but if that doesn't make any sense to you, that's okay. It'll make sense later. The main thing is to see that that you've got this system. It didn't reduce to triangular form, but in fact it reduced to something better for us, right? In fact, triangular form would have given us one solution, and here we end up with actually infinitely many solutions, right? Okay, infinitely many solutions. Anything that looks like this would be fine. So for example, if we take x2 and x4 to be 1, then we see that 1, 1, 2, 1 is in the solution set, right? If we take them both to be 0, we see that 0, 0, 0, 0 is in the solution set. Okay, which you probably knew already, because back here, one obvious solution is to take all of the variables to be 0, and then you're definitely going to get 0, 0, 0, 0. Okay. Everybody okay? Everybody all right? Okay. So yeah, actually I forgot at that point, at the beginning, I should have mentioned that this kind of system with all zeros on the right-hand side is called a homogeneous system. So all the constants, if all the constants here are zeros, then it's called a homogeneous system. And any homogeneous system automatically has solutions. At least that has one solution, right? Because if you take all the variables to be 0, then you clearly get an answer, get something that works. Okay. Yes, Nasir.
Sorry.
No, great. I'm happy.
So if a matrix,
I only wish more people would just ask more questions.
If a matrix
yes.
has like 4, would we still be calling the axis variables? Like for
Yeah, variables. Yeah.
Yeah, if there are 4 columns, so like if there are 2 columns, it represents a line. If there are 3 columns, it represents a plane. If there are 4 columns, what would it represent?
It's just some sort of So it is a space. It's actually a 3-dimensional space in 4 dimensions. Just like you have a plane is a 2-dimensional space. If we had something like x plus y plus z equals 0, well, what's that? That is a 2-dimensional plane in a 3-dimensional space, right? This is just one step above that. It's a 3-dimensional space in a 4-dimensional hyperspace, if you want to call it that. Yeah, but don't worry too much about. Don't get bogged down with what it is. Just count the number of variables. Okay, so let me make one observation. One again, mediocre observation, which is that at this point here, we could have gone one step further and used the, we used this guy to clear out everything below it. We could have used this guy to also clear out above, right? So we could have said, take row 1 and change it to row 1 minus row 2, right? In that case, we would have gotten, oops, we would have gotten 0, 1, 0, 0, 0, 1, negative 2, 0. Okay, so in that case, the system would have been x1 minus 2 x2 plus x4 equals 0, x3 minus 2 x4 is equal to 0, and you see that we basically just done the last work earlier, right? So it's either you do the work later or you do the work earlier. Right? If you do the work earlier, then you get that x1. You immediately get x1 is 2x2 minus x4, and you get x3 is equal to 2x4, right? Which is what we got over there. Yes, Avery.
So I guess this is one of the questions I had while doing the homework, because
Yes.
like there should be multiple ways to reduce to row echelon form. Is there like one specific way that'll get you to the right answer, or should, like, if there's multiple approaches, should you still be getting the right answer with a different approach?
So if you reduce, if you do this last step and get it down to the point where so 4 and 5, so leading entry is 1 in non-zero rows. So, non-zero rows. Actually, I forgot that. So that's actually part of the description of row echelon form. But then there's this last thing that we do. Each leading 1 is the only non-zero entry. The only non-zero entry in a column. So that is, you take the final step and use the pivots to clear out above as well as below. If you do this last step, then the form is given the name Gauss-Jordan form. Gauss-Jordan form. I'm sorry, the process is called Gauss-Jordan reduction, and this form is called reduced row echelon form. Reduced row echelon form. Okay. So we're not going to prove it yet, but in fact, the reduced row echelon form is unique. Okay, so if you go through this process and do this last thing also, then in fact the reduced row echelon form, no matter how you start off, no matter how you do it, you're going to end up with the same answer. Okay, so it's true that yeah. So yeah, but we're not going to prove that yet. Okay, so yeah, I always joke that the mathematician Jordan must be, kind of embarrassed to be associated with just this final step of clearing out above rather than below. This is probably the Jordan from. We're actually not going to talk about it, but there's something called the Jordan Canonical Form. So that's probably the same Jordan, so this is actually a much cooler result than this. Okay. Okay. So okay. So let me just say one more thing. Any questions? Any other questions? Let me just say one more thing, which is that another remark. So this RK means remark. Remark. Any underdetermined underdetermined homogeneous system has infinitely many solutions. Any undetermined homogeneous system has infinitely many solutions, and you see why maybe. If you have an underdetermined homogeneous system, then you're going to have free variables that are expressible in terms of, you're going to have free variables that are expressible in terms, I'm sorry, lead variables that are expressible in terms of the free variables, right? So as the free variables vary, right, you can let the free variables be anything, and that will give you, that will give you your infinitely many solutions. Just like what we have here, right? Your lead variables were expressed in terms of these guys, and you see that you can take x2 to be whatever you want, you can take x4 to be whatever you want, and you're going to get solutions. So you get infinitely many solutions. Yeah,
Is that true of non-homogeneous systems too? Like
No.
if you're underdetermined?
Yeah, actually, no.
Finite solutions.
Can anyone see that it actually, anyone think of an underdetermined system, underdetermined non-homogeneous system that doesn't have any solutions, say? So you could have something like x1 you could, so just think in space, let me say it this way. In space, you could have, two planes. No, sorry. No, yeah, in space, you could have two planes that don't intersect each other, right? Well, that's an underdetermined system, but it has no solutions. Okay, so think about what's happening geometrically. Why does homogeneity force you to have solutions? Well, because they're
They intersect.
going to intersect at 0, right? The planes would have to pass through 0, right? And so you're going to have infinitely many solutions, right? Because you're going to have a line, right? Okay, or you'd have a single point at least. But if it's underdetermined, you'd have a line. Yes, Liz?
So underdetermined means more variables than there are equations.
That's right. More variables than equations. Ross, did you have a question?
I have the same question as
The same question. Okay, yes.
So then a homogeneous system is only zeros in that column?
That's right.
What if they're all ones?
That's not.
That's not.
No.
But wouldn't
So
then,
all
but wouldn't
zeros.
then, just like how a homogeneous system, they all pass through 0, wouldn't, if it was all 1, they all pass through 1?
No. If you think about it, that's not the case, right? If these things are all zeros, then certainly setting these each to 0 will give you a solution, right? So
Right.
right. So this is the system. Okay. So if you set all the variables equal to 0, you get 0, right? But if I set all the variables equal to 1, I don't get 1.
Right.
Right?
Yes,
So
okay.
it's not that if 1, 1, 1 is here, then setting all the variables equal to 1 will give me a solution. Okay.
That sounded stupid when I.
No, it's okay. It's okay. No. You're seeing a pattern. You're attempting a pattern. It's wrong, but but that's okay, right? I mean, that's what you got to do. Yeah, Avery.
I don't understand how geometric, I understand how they all pass through 0,
Yeah.
but then I don't understand how they could have infinitely many solutions. If planes were just intersecting at 0, wouldn't they just intersect at 0? How could they?
Because if you have an underdetermined system in R3, that means you have two planes,
Oh, and then
two
they
planes,
just
right?
like are the same plane.
Two planes passing through the origin. So there's a plane that slices through the origin. There's another plane that slices through the origin. Okay, two planes will intersect in a line, right? If two planes intersect at all, they intersect in a line, or they're completely identical, right? So you either get if they're identical, you get a whole two-dimensional solution set. If they're not identical, then you would get a line of solutions, which is also infinitely many solutions.
Okay.
Okay. Okay. Okay. Okay. Okay. Let me go on. Let's go on to section 1.3. This should be called probably basic matrix notation and algebra. Matrix algebra. Okay. Okay. So this what we're going to say for the next, I don't know, at least the rest of the class and maybe the beginning of the next class won't be particularly exciting. It's just notation. Okay, but we have to do this notation. Okay, so and we have to get used to this notation. Okay, so what's a matrix? Let's start off. What is a matrix? Okay, it's just an array of numbers. So it'll be something that looks like this: alpha 1, 1, alpha 1, 2, alpha 1, 3, alpha 1, 4, up to alpha 1, n, alpha 2, 1, alpha 2, 2, alpha 2, 3, alpha 2, n, dot, 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 alpha m1, alpha m2, alpha m3, alpha mn. Okay. So, so we will usually abbreviate this sort of thing by just writing alpha ij, where I ranges from 1 to m, and j ranges from 1 to n. And we usually denote this by some capital letter. A. So here we're going to use, for example, A. Okay, so this one, you see that it has m rows, and it has n columns, right? And so we call this an m by n matrix. Okay, and we sort of write that concisely by saying that A is in R m cross n. Okay, so this thing here we use to denotes the set of real m by n matrices. Yes.
Can I go to the restroom?
Yes, of course. Yeah, thank you for asking. I should- Okay. So let me not spend too much time on this. So mark. If it's an m×1 matrix, it's also called a column vector. A column vector, right? So if it's a matrix with just one column, we'll also call it a vector. If it is a 1/n matrix, it's also called a row vector. Okay. Some basic definitions. So first off, we say that two matrices A and B are equal we say matrices are equal if they're the same size, if A and B are have the same size, so they're both in the same size matrices. They're the same size, and alpha ij equals, aij equals bij for all I and j. In other words, all entries are equal. Okay. So I should probably write A is the matrix aij and B is the matrix bij. Yeah, listen.
So what is that arrow
Oh, sorry,
between?
this guy. So this means for all. It's actually an upside down A.
Okay, but I mean the one between B and
Oh.
R.
Yeah?
Yeah.
Okay, that means is an element of.
Okay.
So back here, so A is an element of the set of real n×n matrices. Okay. So this is so set notation. Like if I say Lizzie is an element of the students in Math 60. So there's a set of students. You are one of them. Okay, that's all it means. Like if I say you are not an element, that means you dropped the class, right? Or maybe you haven't enrolled in the class. I'm not an element of that set. So just set notation. Okay. Okay, so we say, so yeah.
What does the upside down A mean again?
It means for all. So let me read this in English. So we say that matrices A and B are equal. That A equals B in notation if A and B are both elements of the matrices, the m×n matrices. Okay, so they're both m×n matrices. They're both the same size. Okay, so what we're saying is they're equal if they're both the same size, and two, all their entries are equal. So aij equals bij for all I and j. Okay, and to be completely proper about this, I should probably say for all I from all I between 1 and m, and all j between 1 and m. Okay, because you might say for all I and j, my daughter, no doubt, would say, but what about if m, what if you're bigger than m? Okay. Not that she understands this, right? But she would, if she understood this, she would definitely point out that I'm being imprecise. My daughter is 9 and kind of like very, very literal-minded, extremely literal-minded. Always willing to point out that I've stated things imprecisely. Okay. Okay. So, right, matrices are equal if they have the same size and all their entries are equal. Okay. So we don't say, for example, 1, 2, 3, 4. We don't say that this guy is equal to that guy, right? Even though the corresponding entries are equal, they're not the same size. Okay. So they're not equal to each other. Right. Even though the entries are equal, sure, this guy's entries are equal to that guy's entries, but they're not the same size. Okay. 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 2, addition. If A and B, if A and B are both the same size, we define their sum, A plus B, to be the matrix, the m by n matrix C, where with entries Cij being just Aij plus Bij. So you just add the corresponding. You just make a matrix of the same size where you've added the corresponding entries. So 1, 2, 3, 4 plus 1, 0, 0, 0 is going to be 2, 2, 3, 4. Okay? You just you make a matrix of the same size where you add the corresponding entries. Right? 1 plus 1 is 2, 2 plus 0 is 0, etc., etc. Okay, so this is matrix addition. Matrix addition. Number 3 is called scalar multiplication. Scalar multiplication. Okay, so if A is an m by n matrix, and alpha is some number, so alpha is an element of the real numbers. Alpha is a real number. Then we define alpha A, right, the scalar, to be the matrix, again the m by n matrix with entries alpha Aij. Let me say this way, to be the matrix C with entries Cij being alpha Aij. Okay, so just multiply every entry by the number. Okay, so if I have 5 times 1, 2, 3, 4, well, that's just going to be 5, 10, 15, 20. Right? So you multiplying a matrix by a number, you just multiply every entry by a number, by that number. Okay. Number 4, the zero matrix. The zero matrix is the matrix of the appropriate size with all entries equal 0. Okay, so you have some sort of zero matrix where A plus the zero matrix is still going to be A. we have additive inverse matrices, right? Additive inverse, right? Just like you have numbers and negative numbers, right? You have a number, you have a negative number, they add up to 0, right? When we write negative a, we mean is negative 1 times a, right? Where you take all the entries and take their negatives, right? So that a plus negative a equals the 0 matrix. Okay. So what we're doing is basically setting up something to think of matrices as some sort of generalized number, right? Right. You've got this generalized number. You want to talk about what it means to add these numbers, right? What does it mean? Well, you just add them entry-wise. What does it mean to multiply them? Well, we have sort of a lame version of multiplication at this point. We just say, well, we can multiply the matrix by a real number. And what we mean by that is to multiply every entry by that number. Okay. We'll get to a better version of multiplication in just a minute. We have a 0 matrix. We have something corresponding to 0, something that when you add it to something, then nothing happens. We have something like the negative numbers. Okay, so the way you want to think about this, it seems kind of dull, but what we're doing is basically setting up an analogy, right? That these things are something like numbers. Okay. But not exactly. Okay. Okay. So we're going to describe multiplication, but before we get there, we're going to need some useful conventions of the author, which I think are pretty handy. So these are things that the author uses, but they're not usual. I don't see these in other books. Okay. So the author's conventions, and they're good ones, I think, are one that column vectors are denoted with bold-faced, bold, lowercase letters. So if you see something like X, Y, Z, so the way that mathematicians write a bold font is to sort of put a double strike on some element of it. So if you see something like this is going to mean a column vector. Okay. Row vectors by the same sort of thing, but with an arrow above. So arrow above. Okay. So if you see anything like this, you know it's a row vector. Okay. Okay. So if A denotes the matrix Aij, that's to say A11 through A1n, AM1 through AMN. Oops. So here's a kind of odd but again useful thing. AI, so a bold AI with an arrow above it denotes the ith row. Denotes the ith row, so that would be AI1, AI2, AIN, and AJ with no arrow above it denotes the jth column. So A1J, A2J, down to AMJ. Okay, let me just give you an example of that. That seems kind of strange, but you'll see how useful it is. If A is the matrix 3, 2, 5, negative 1, 8, 4, and I write A2 with an arrow above it, then that means the second row, right? So that would be negative 1, 8, 4. If I write A2 like this, then that would be the second column, so that would be 2, 8. Okay. Okay, so so we can abbreviate A as either column 1, column 2, column n, or first row, second row, nth row. Okay. Okay. I know this seems like why it seems dull, but it'll be very, very useful in just a moment and throughout the first part of the course. Okay, so I think actually I'm going to stop there. So the reason we set up this set of notation is to easily define matrix multiplication. Okay, but there's just 1 minute to define matrix multiplication, and I don't want to rush it. So just remember this notation, right? This is the most important part of this last section. This notation. Okay, so if you see something like this is a row vector. The second row of the column, second row of the matrix. This is the second column of the matrix. Okay. So next time we'll talk about matrix multiplication, and then we'll start doing some more interesting stuff. Okay. Okay. See you all next time.